Good day to everybody. Thank you for joining us for today's webcast. And it is a really exciting webcast. We're going to be talking about mastering event sourcing, a game-changing design pattern for distributed systems. So we've all been, building and running and maintaining and improving distributed systems for quite some time now. I think we're always interested in evolving our approach, refreshing our strategies, and taking a look at new patterns out there. And so I'm excited to be joined by Kevin Hoffman, and we'll get to Kevin in just a few moments. A couple of housekeeping items very briefly before we launch into it. Your lines have been muted, but we are very interested in your comments and questions. So please use the questions part of the GoToWebinar control panel to log those questions, and we'll get to those at the conclusion of today's webinar. Also, the slides for the webinar and the recording will be sent to all that registered for the session. So be on the lookout for that after the conclusion of today's webcast. I'm very excited to introduce today's speaker, Kevin Hoffman. Kevin is the Director of Product Management at Akka, author of the book Real World Event Sourcing, and a longtime fan and practitioner of event sourcing. He has worked with some of the largest enterprises, helping teams build cloud native and often event sourced applications. So Kevin's got a great mix of content and demos for us here today. So Kevin, welcome to the webcast.
All right, thanks for having me. So let's get right to it. Of course, there we go. So my goal for this isn't to teach everything there is to know about event sourcing. It's kind of hard to cram into one webinar, but if I can get people inspired and curious enough to go off and start tinkering with building event-sourced applications, then I'll consider my job successful. So I'm going to start by talking about some of the problems we have today in building distributed systems. Then I'll talk about some of the solutions that we've developed over the years. And then thirdly, I'm going to talk about how event sourcing is almost a formalization of some of the patterns, practices, and rules for dealing with distributed systems problems. And then I'll get to the demo, and then finally the important part will be Q&A. So building distributed apps is hard. That's an understatement, obviously. Probably the first real problem with building distributed systems is that we have multiple sources of truth. If your application isn't a monolith sitting in one place, then by definition, you have multiple sources of truth. And so we have to deal, whenever we're building these apps, we have to deal with figuring out, which of the many sources of truth to trust first or most. We've got data coming in from the edge, data coming in from mobile applications, data from the cloud, conflicting data from multiple sources. And then another pattern we see a lot is we derive a second level or more of data from the low level data. And so now you have conflicting sources of truth being used to build yet another set of data, kind of compounding the problem. The next is a lack of an audit trail. When we build traditional CRUD style distributed apps, what we end up with is we have state, but we don't know how we got there. We don't know why the state is the way it is. And we often don't even know when the state became the way it is. And what happens with the day 2 and beyond problem with building and maintaining these distributed apps is we can't recreate the state based on new logic. So we can't go back in time, change how we calculate interest or whatever, and then regenerate our new state. We're kind of stuck. And along with that, we can't really run what if scenarios. We can't take a look at our new logic, apply it to our old state, and then see what it's going to look like. The other issue with distributed applications is obviously they're distributed, and that generally means we have concurrent writes. And historically, we solved the concurrent write problem by using the last write wins strategy. So we just write the data, and whoever gets there last wins. The problem with that is that the last writer may not have been based on the most up-to-date information. So you could end up, and frequently do end up, overwriting the state we should have with out-of-date state. We can solve some of this with optimistic concurrency checks, but that's not a panacea. So we end up with a situation where we own the complexity of dealing with conflicts. And so we go off and search Stack Overflow and everything else for techniques that we can use to solve this problem. And then we end up getting into a quagmire dealing with conflict-free replicated data types. Worse yet, we roll our own leader election system, and more times than I can count, we end up in where we just write our code, and if it doesn't work, we retry, and we just keep retrying until it works. And that's what I generally refer to as hope-based consistency. And then probably the worst offender of all is distributed transactions. And they're a whole different class of problem. So with the way things are today, we generally spend 10% of our time dealing with and being able to actually write features, the things that our app makes money off of. And then we spend 90% of our time on all of the busy work and logistics and nightmares of dealing with distributed systems. When we are writing these applications and we're storing the data, generally we store them in kind of in a normalized or relational format. So we write the data in a way that's optimized not for a user, but for the database or something else. And so we try and fix that problem by maybe moving the data out closer to the edge to make those queries run faster. But now when you move the data into multiple places, you add even more sources of truth and consistency issues. And we think, well, maybe we'll add a cache layer to fix it, because we all know that if you slap a cache on things, it just makes everything better. But then, we have more complexity, and now we have to maintain our app and a cache. So just storing data in a distributed application is a much harder problem than people initially think. So how do we get around some of these problems? The first is obviously to get rid of all of the conflicting sources of truth and just have one. Obviously, that's easier said than done, but if we treat everything in our system as an immutable event, as a record of what did happen, not what failed to happen or what might have happened, then we have an eventually consistent system. But that data, because it never changes and it always means the same thing regardless of where it was, we can now replicate this source of truth everywhere we need it without adding conflicts. And probably the biggest thing here is that when we have one source of truth, we're no longer writing our own reconciliation and conflict resolution systems, because we want to be in the business of writing features, not conflict resolvers. Everything needs to be, we need to embrace the idea of eventual consistency. And, eventual consistency essentially means that when I write data as part of somebody using my application, that change will eventually be visible to all the other parts of the application. And so we want to be able to identify which data can be slightly out of date or eventually consistent, and which data can't. And in many cases, we find that eventual consistency is just fine, and we don't need strict consistency. But by embracing eventual consistency, it forces us to decide which things need strict consistency or strong consistency and which things don't. And if you've used a social networking app and you've hit like on something and that doesn't actually appear until a little bit later, you've seen eventual consistency. And there's a whole bunch of other examples. Some consistency is far less available than other. You've got banks that don't give you your updated information until the end of the day. Airlines that may never give you your updated information. The other thing to do is get rid of distributed transactions. We have historically had these centralized distributed transaction managers, and we figured that would solve all of our problems. And it actually just gave us another source of problems. Distributed transactions make us feel like we have control over the system, but we don't. And we then need to figure out, what's going to happen when our rollback fails. So if we try and commit a transaction, that fails. We try and roll it back, that fails. Now we have no idea how to get back to a stable state, especially if we don't have an event log. So one of the other things that we do in order to get rid of some of the complexity and problems with distributed systems is we can generate the query results before the users need them. And by that, I mean, if we know how people are going to use our applications and we know what information users are going to need and when and how they're going to need it, then there's no reason why we can't have that information ready to go before they query for it. So this means that when a user wants some data, we don't need to go off and do a join across multiple tables with complicated, slow filtering and table scans and locks. Instead, we can just have the user ask for the data they need and we can give it to them. And what this ends up doing, the impact on us is when we go to write the data, we can then also write the data into materialized views or places where we're storing the data in a way that's essentially ready for query. And so the inverse of the chart that I showed a minute ago is we want to be able to spend time on the right things. So we want to flip that 90-10 ratio and spend 90% of our time working on features and only 10%, or hopefully less, working on the grunt work of dealing with distributed systems. So as I mentioned, if we take a look at some of the patterns that we've got for dealing with the complexity of distributed systems, and we kind of formalize those into some rules, what we end up with is event sourcing. And before I keep going, I think it's probably worth pointing out that event sourcing with a capital E and a capital S is sort of the formal definition of how to do this particular type of application. There are looser definitions like event driven, event backed, event based, even just calling a system reactive. And as you'll see, some of the problems come from partially implementing event driven systems and not following through with all of the additional rules from event sourcing. So an event sourced system basically boils down to two functions. We apply this function to our state and hand it an event, and the result is new state. So my state might be my bank account ledger, and I have an event that, indicates that I'm depositing some money, and the new resulting state is my ledger with that money in it. And additionally, we've got a function for dealing with commands. So we take our state, we validate the inbound command based on that state, and then we produce events as output. And there's a bunch of reasons why this ends up being such a game changer. One of the biggest ones for me is that now everything is testable, and it's testable in isolation and predictable. And even better, when we build an event sourced system, we spend less time writing code. We write smaller amounts of code, and we get the ability to go from my local laptop to a globally replicated solution without having to change any of our code. And that's pretty huge, especially if you've been through the pain of trying to convert something that worked locally to something that works in the cloud. So there's a number of building blocks, the sort of Lego bricks of composing event-sourced applications. Obviously, the first is events and the event log. And again, that is an immutable list of things that happened in the past. So you'll see all of those are they're named as past tense verbs, like amount deposited or user logged in, things like that. Commands, entities, which are similar to the DDD concept of an aggregate, views, workflows, and producers and consumers. And I'll get into each one of these as I go. So commands are a request to produce an effect. So I'll issue a command like deposit funds to an entity, and if that command is valid, that entity will then issue out the corresponding events, like amount deposited. Commands are ephemeral. They don't exist, and this is one of the big sources of trouble that I find happens a lot when we halfway implement event sourcing, where we store commands, and then by storing commands, we create all sorts of consistency problems, and we're essentially back to square one. Events, as I said, they're an immutable representation of something that happened in the past, and pretty much everything that exists in the real world is event sourced. And what we find is that modeling things as an event sourced domain is generally easier than trying to enforce our own, consistent view of the world onto external things. Entities, these are the two functions that I showed. They apply events to state to produce new state, and we handle commands to produce a list of events. Views. So as I mentioned, dealing with distributed data, multiple sources of truth, and eventual consistency, what we end up with is this concept of views, which are data that's in query-friendly format. So if you're familiar with the CQRS acronym, views are the read model. If you're a functional programmer, then you can think of views as a left fold over the event stream to produce some piece of state. Views can be easily evolved, which is another really big benefit to developers building these event-sourced applications. And views, because they're they're freestanding. They can have their own scale, resilience, and replication requirements different than the strong, consistent portions of the application. That gives you much more control over, how much compute you're actually using. Workflows manage long-running processes, and long-running here doesn't necessarily refer to an amount of time, but it refers to a number of events. So if there is a workflow that starts with a stock item received event and finishes with a stock item purchased or sold event, and there's something that needs to happen in the middle, workflows are what we use to manage those things. So we can use workflows for shopping carts, like I said, order fulfillment, putting things on hold, like reserving airline tickets and then purchasing them afterwards, where the reservation starts the workflow and the purchase finishes it. And finally, sort of a visual way of showing that on the left, we have a bank account and a balance, but we have no idea where that balance came from, whether it's accurate, and the sequence of events that led to that. While on the right, we have a ledger, and so we know exactly where its current balance came from. So event sourcing comes with a number of rules. Not all of them are listed here. More of them are in my event sourcing book, but these are the ones that I think are fairly key, that if broken, will mean the difference between a successful application and a failed one. The first is events can never be modified. Um, and that also refers to schema. So you can't change the shape of an event. If you do, it's a new event or a new event type. Never read the wall clock for state. That means that if you have any logic in your application that needs the concept of the current time, that time needs to have come from a stamp on an event, and you can't read the wall clock time from the operating system. There's a number of reasons for that, but the biggest one is that as soon as you touch the wall clock, your business logic is not repeatable, your event stream is not idempotent, and you no longer have consistency and predictability. For the same reason, don't ever use random numbers by getting them from the operating system. This one's generally harder for people to follow, but one really good way to deal with it is to put a seed on the event. And then when code that requires random numbers needs a random number, it uses that seed. This makes it so that even though the code is using so-called random numbers, the same event will always produce the same output, no matter how many times you replay it. Another important one is not modeling a failure to create or failure to do something. Obviously, there are some exceptions there, but by and large, you want to model your events should represent things that did happen, not things that did not happen. And then never produce side effects when processing events. That should be fairly straightforward. If your code produces a side effect during event processing, then the code is no longer testable, predictable, or reproducible. So now that we've got the beginnings of a formalization of event sourcing, let's take a look at how to build applications, event-sourced applications with Akka. And as we'll see when I get through the demo, it is surprisingly easy. If I'm already modeling my application as, in terms of event-sourced concepts, then those map directly to the types of components that I need to build with Akka. So Akka has a very simple developer experience. Like I said, if I model my event source domain, then I have less code. The code is easier to maintain. And more importantly, there's less stuff that I need to cram in my head and maintain in my head in order to work with the code base. It's very easy to work with. And then obviously what I want to do is let the experts deal with deploying, distributing, and so on. Obviously, I want to verify that those things are being done properly, but the key is that there's nothing in my code that in any way at all relates to deployment, distribution, and so on. It's just a pure event source domain. So I'm going to run through a demo here. And this demo is a chess application. And one of the things that I like about chess as a sample is that the state of a chess game is essentially a function applied to the list of moves so far. And so it lends itself really well to being an event-sourced application. And so what I'm going to do is go through and show the application and then switch over to the event-sourced code that produced each one of these things. So first thing is you can see that I'm logged in, and logging in is a command as well. And no, that's no good. My browser likes to expire tabs on me, which is rather annoying. So I'm going to show the Java or the chess domain, and we'll take a look at the player entity, and you can see that I handle the player logged in event, and see if that works. Yeah, here. When I log in, all I'm doing is producing new state. And so what's important here is you don't see anything about database storage or distributed systems or locks or concurrency or any of the things that we typically hate. And it's just what's the new state as a result of a player being logged in. And if I look at the player entity here inside the Akka console, you'll see that this is the current state. This is me. And I can look at the events that produced that state. So I received a player logged in event, and that's the logged in event right there. And that produced this state. And so I can go back to my chess service. And so that's the player entity as it stands now. And you'll also see that the lobby entity doesn't exist yet. So what I'm going to do is go to the lobby and start a new match. And this starts a game that is awaiting another player. And this was done by by sending the start lobby match command. And you can see in the lobby when a pending match is created, again, I'm adding to my current state. This is all just pure, functional Java. Again, there's no side effects in here. And so now if I go back to my lobby entity, you'll see I now have a lobby and I have a pending match. And as usual, I have the event that's responsible for the lobby's current state. So I'm going to cheat slightly in that I don't have another person to play. So I'll use, this is in my UI, by the way, so this isn't, so what the code that I'm doing here isn't all that important. Get lobby matches. So I'm going to get my lobby matches. And here's the join code. So if I wasn't doing this by hand, imagine you can just send this code via QR code or something else to the player that you want to play with. So I'm going to join a lobby match here. I just happen to know the GitHub ID of our CTO and the creator of Akka, so that worked out nicely. So player ID and the match code. So now I have I now have this match that's been joined. So if I look back at the lobby, a workflow running managed by Akka has removed the lobby match, and now I have a real match. So if I go to my matches list, you'll see this is the match now has me versus someone else. And again, these were everything that's been done so far is always the result of sending a command to an entity and then dealing with the output events. There's no more complexity to it than that. So now I have my my chess game, and the state, as I said, the state of a chess match is the sum of all moves. Since there's no moves, things are still at the default state. As you can tell from my unbelievable CSS skills here, I've managed to indicate that it's my turn. And I'm going to move my knight out here. So my knight's moved. You see this move list now includes knight to c3. And again, this move list is literally the event stream for a given match. And so that's pretty much all there is. If I go back here and I look at let's take a look at the match entity. You'll see that I can send a command. So there's a command create, and if the validation passed on that command, then I will persist a match started event. If I want to finish a match, same thing. If the validation passes, or in this case, if the validation fails, if the validation passes, then I persist the game finished event. And so you can see that if I model things in terms of commands and events and views, so if I go back to my matches list, what I'm looking at here is a view. I'm not reading data from a database. I'm not doing joins in order to get this person's name and this person's name. I have a match view that has my real name in it, has Jonas's real name in it, everything that I'm going to need queried for me ahead of time. And so this view can be potentially eventually consistent, but what is even more interesting is that I can, if I want to run this service in multiple regions, I just click activate region, and it shows up there. And my data is now being replicated across regions. And if one region fails, the other region takes up the slack for me. I don't have to worry about, you know, where is my RDS instance running and how, how do I avoid a bottleneck on a big central database? With Akka, there is no big central database. There's just an event stream and the stuff that gets produced as a result of that event stream. And you can see that this application is exposed at this URL. There's 3 instances of my app running. So, no matter how many times I hit refresh on this, doesn't matter. Those instances are going to get the same data. And there was one other thing I wanted to show, which is now if I look at the chess endpoint here, this is my chess API, and the Akka console sees all of these endpoints in it. But what is even cooler about it is if I show the implementation of this endpoint, there's a couple things in here that are pretty powerful. The first is this endpoint is available to the internet. The second is in order to use this endpoint, I require a JWT, and I require that it be issued by an issuer named ChessWeb. And I have keys set up in my Akka project that allow me to do this kind of validation. And this, it's hard to express how much time this actually saves, but there's a, this is all just taken care of for me automatically. And I have, my chess endpoint and a nice way of setting up the routes. So that should be everything, and should be, hopefully there's enough, I didn't go too long, and there's enough time for questions.
Yeah, fantastic stuff, Kevin. Thank you. And lots of great questions have come in, so let's jump right into those if that sounds good to you.
Yeah,
Okay.
are you gonna pick those, or do you want me to pick them out of the bucket, or how does this work?
I'm happy to just kind of go through them. If there's any that you'd like to start with, certainly we can.
Okay. Let's see. I don't see any in the questions panel, at least on my side. So
Okay, then that makes the decision easy.
yeah.
All right, first one. You've stated that query side should not be used for the decision making. But what if I need to make a decision on multiple aggregates? Or even if I need to find the aggregate by some filter on internal field? Without the query, it will be problematic to load all the in-store memory.
Yeah, there's the typical answer is obviously it depends, but there's a couple of ways that I typically tackle this. One is if I need to make a decision based, and that by decision, that decision is based on fully consistent data, where I don't want, in this case, I'm not going to make a decision based on eventually consistent data. Then what I can do is create a new type of entity that subscribes to the events from other types of entities. And when it handles those events, it can maintain its own internal state so that that entity can then be used, or the state of that entity can then be used to make decisions. And then, views, there's an asterisk there. You can make a decision based on a view if you're okay with the decision being based on potentially stale data. So hopefully that answers the question.
Perfect. Next up, in a distributed environment, how many distributed components should be allowed to write to the event log?
So that is, there's a a high level answer to that, and then there's the really low level details behind all of the amazing stuff that Akka does for you. The interesting part is when I go and uh, if I have, if I go back to my application, my lobby entity here, you'll see I'm persisting some of these events. So like I'm persisting a pending match created, or um, I'll persist there's another workflow, which is an interesting one, where if a pending match remains unjoined for more than 5 minutes, Akka will let me expire it. But if you're using the Akka SDK, then you call persist, and you are guaranteed that the event that you're persisting will um, be written to the event log, and Akka will take care of making sure that the right sequence is applied, the right timestamps are applied, and that the event is replicated to all of the regions where your service is running. So the short answer is, as a developer building the components, you don't have to worry about it. The detailed answer is there's some really, really in-depth computer science distributed system stuff underneath that makes all that work.
Okay, great answer. Thank you. All right, next up. When rehydrating an actor from event logs, maybe due to service restart, is there any pattern that says I should not try to bring back to life actors that are considered as expired in order to reduce memory for such inactive actors whose data was once added to the event logs?
Okay, I'm not sure if I fully understand the question. Let me see if this is it.
Okay.
So the question is, how do I control, or can I control, the rehydration of passivated actors? And
Yeah.
um, what are the consequences of that? So the good news is that if you're using the Akka 3 SDK, you don't actually interact with actors directly at all. It's just entities. And the SDK deals with trying to figure out, when to passivate and how to deal with all of that. The when Akka decides to instantiate your entity, it will feed your entity the event stream that is up to, the most current. So you don't have to write code that is aware of whether or not a restart occurred. So it's been a while since I've used the really low level Akka stuff, but if I remember right, there's code that you write in an actor system that where it's visible in the code that you are recovering from a restart or something like that. And in the Akka 3 SDK, you don't see that. So all you do is write the logic for how you're going to mutate, or how you're going to change your state based on the event. And Akka then takes care of instantiating your entity, figuring out where the entity should go in the cluster, and when and how to feed that entity its event log.
Okay, thank you. Next up, can you walk through an example of how to handle async side effects? If my system needs to reach out and make something happen that can fail and would require compensation actions and crash recovery and so on.
Okay. Yeah, there's a couple of really good patterns for this. Generally, I like to think of the Akka 3 event sourced service as a hard boundary, and where everything inside it is, this ideal side effect free, predictable environment. As soon as you want to go outside of that and interact with the messy, unpredictable real world, There's a couple of ways you can do it. One is you can publish messages to a topic, and I have one of those right here, possibly. Yes, so you can basically what I'm doing is I'm taking events from the lobby entity, and then I am publishing them to a topic called chess events. And that topic is configured as a broker inside my Akka project. So I go to settings, integrations, you'll see I have Google PubSub in here. And what that means is that this absurdly tiny amount of code consumes from, the consistent internal world and then publishes to a GCP topic. And then I can then have all of the unpredictable side effecty code I want on downstream on that topic without forcing my Akka code to attempt to model side effects internally, which you should never do. Other things you can do are, I'm not sure if I have one of these in here. Yeah, you can set up a consumer where when the consumer receives an event, you can do something side effecty, and then it's essentially on you to determine whether the side effecty thing that you're doing is idempotent, because the guarantees inside Akka are going to be that you've got at least once delivery. So you need to be aware of the fact that as soon as you get past that hard boundary around the service, that things again become more traditional distributed systems, and you could theoretically get the same message twice.
Okay, let's change gears a little bit. How would you migrate an existing application's data without a reproducible event log into a new distributed system?
Okay, so you've got a legacy application that has, for lack of a better description, CRUD style data that has no event log, and you want to figure out how to move that same data into an event sourced service. Is that
Yeah.
okay? The cool thing that there's a couple of ways to do it. Usually the way that you want to have an event sourced system ingest information from some other external source, there's a couple of things. One is you can, as I showed, you can consume from a topic. So in theory, you could put all of your existing data onto a Kafka topic, and then you've got a consumer that pulls things off of that Kafka topic, and then in response to that, it then uses commands on internal entities, and that will sort of pull all of your data from one place and then give you an event log. Obviously, the event log isn't going to reflect, how long it took to accumulate that old state, but it's still a way to get that data in it. Another way to do it is just to write, a script or something that consumes your existing data and uses the Akka 3 component client to ingest those as commands. The super short version is that the only way you should ever have events appear in your event sourced system is by having sent a command to an entity. And I don't know enough about the existing architecture, but another option is to not migrate that data and you can leave that data up behind a service boundary or something else. But if your goal is, I have a stateful model now, and I want to model it as an event-sourced system, but I want um, to sort of precede my new event-sourced system with existing data. Then in that case, I think uh, the you can go the topic route, or you can use some sort of script or whatever that uses the Akka 3 component client to issue commands.
Okay, thank you. Good answer again. Question here about interested in knowing how to time travel, meaning looking back at, in this particular case, the state of financial transactions last month to produce month-end balances. Currently, we record daily states, and the attendee adds it's not very good.
Yep. So obviously this is going to vary depending on your domain, but things like monthly reports that are really good candidates for being views. So one thing you can do is as transactions come in, and these might be low-level transactions, you have a consumer that's looking at those transactions and performing, sums or averages or, rolling windows or whatever on the view that it's building. And inside that view, you have a number of options. You can create a view per month if you want to do it that way, or you can have a view where you supply the month as part of the query. Let me see. I can show you what a view sort of looks like, and then so here I have a match archive view, and the match archive view is over time logging all the moves that occurred within a match, and then when it's done, um, it's sort of sent off. And if you look at the view, I'm building, straight up functional Java state, but because of the way Akka lets me do things, I can write a query where where I'm looking for a particular player in this case, but in yours you might be looking for a given month and year, and you can use one of these queries to pull the month and year out of the view that you've been generating. And like I said, there's a couple of options there. You can store all of the historical stuff in one view, or you could have those views as more like this, where you're going to filter on certain columns. It's You just have to figure out what your trade-offs are going to be based on how much data you're storing that you want available to these views versus sort of archived in cold storage, what your growth rate is on the data that you're storing, all those sorts of things. But a short version is you can create views that are joins of events from multiple entities, and that's a really good way of automatically generating these sort of month by month reports. So instead of thinking of it as going back in time, think of it as generating these monthly reports on the fly.
Interesting. That's a good way to put it. All right, lots of questions here. Let's see how many we can get to before the time's up. What can I do if my system is event sourced, but I require to provide a facade that has read after write consistency?
That's an excellent question because the chess game has read after write consistency. So let's see, if I look at, well, first I'll take a look at the API and I'll show you the endpoint. Inside the endpoint for my matches, you'll see, yeah, get matches. Nope. Lobby entity. Yeah, this is it right here. So the lobby, when I look at this, this is the list of pending matches, right? And uh, as soon as I create a pending match, that data is available immediately, and you can see it in the chess application. And if you look, you'll see what I'm doing is I'm calling get pending matches on the lobby entity itself, and I'm not using a view. So if I look at the lobby entity, uh, get pending matches here is, look at this, I'm just, give me my current state, call the pending matches function on it. And the pending matches on the lobby object, which is in domain, you'll see here, yeah, it's in here somewhere. But anyway, again, all of this stuff is just, Java records, and Akka is taking care of the persistence. But again, to sort of recap the answer to the question is that if you want eventually consistent data, query it from your views. If you need consistent data, query it from the entity, because you're guaranteed that if your command was received successfully by the entity, its state will have updated before you make your query.
Okay, thank you. And then maybe time for one last one.
Okay.
What are the primary domains of your recent projects with event sourcing applied? Any domains you would not recommend using such an approach?
Uh, so for samples, I've used, chess, the shopping cart sample that we have. Banking is always a good sample domain. One of the domains that was my favorite was, uh, without giving away any specific details, and this was prior to me being at Akka. There was think about a small event sourced system sitting on a device out on the edge, so physically in the field. And so there was an event source system on thousands of these devices in the field. And then there's an event sourced system sitting in the cloud, and used a topic publisher to uh, get events from the edge into the cloud. But there was sort of not just a rate limiter, but there's a bunch of really, really fast data happening on the edge. And then the topic publisher was essentially only sampling like 1 out of every 100 of those events, and then sending it up to the cloud for more processing. Short answer is, I think event sourcing is applicable to every domain. I don't think there is a business domain that cannot be modeled as events.
All right. Well, scorching hot take there. We can close the webinar with that. There's a few other questions that we didn't have a chance to get to. So thank you all for your time and participation and attention here. And of course, thank you to Kevin for sharing some of his expertise. With that, stay tuned for the recording and slides coming to your inbox, and we will see you next time. Good day, everyone.